All right, this video is about basic graphs, and this is the beginning of our pre-calculus course, and it begins with a refresher of college algebra. So hopefully you remember this from college algebra. There are some basic graphs that we refer to very frequently from now on in your math life. The first one is y equals to x, which is a line. The next one is y equals to x squared, which is a parabola. And then we have a cubic function, y equals to x cubed. So these are all examples of polynomials. Those three are. Y equals to the cube root of x, y equals to 1 over x, a rational function. This is a radical function. Cube root of x is radical, 1 over x is rational, and the absolute value of x. So I'm just going to go through these to remind you how these work, what they are. If you are ever like, I can't remember this from memory, what these look like, you can always point plot, where you put some values in for x. So for instance, here's an example. You can do this on any one of these, but for y equals to x, this I know to be a line for a couple of reasons. One, it fits the format of y equals to mx plus b. If you look at this, y equals mx plus b. This is the slope-intercept form of a line. It fits this format. This is 1x plus 0. Those are the numbers I could put in there. This is telling me it has a slope, change in y over change in x of 1 over 1. The slope is 1. And a y-intercept of 0, meaning that the y-intercept is at 0, 0. So that is a line. The other way you can tell if you're dealing with the line is the highest degree of any term will be 1. That will be the highest degree. So the highest degree of this variable is 1. And so that also meets that criteria. So y equals to x is a line with the slope of 1 and a y-intercept of 0. So if I'm right here at 0, 0, right here, then and these are some points on my graph. I could rise 1, run 1, up 1, right 1, and get another point. I could do it again, up 1, right 1, and get another point, and connect the dots, and this is the line I would get. And so this is the graph of y equals to x. What I did here, but you could also put in some points. When x is 1, y is 1. When x is negative 1, y is negative 1, and plot a few points and connect the dots. For this y equals to x squared, we know this is a parabola, but if you wanted to put in some points, maybe 0, 1, 2, negative 1, negative 2, you could get some points here. When you put in 0, 0 squared is 0, 1 squared is 1, 2 squared is 4. Negative 1 squared is negative 1 times negative 1, which is a positive 1. Negative 2 squared is positive 4. So we get the point 0, 0. We get the point 1, 1, 2, 4, negative 1, 1, negative 2, 4. And so we get this parabola like this. That's a basic graph you want to be familiar with. X cubed, you cannot do the same thing. I'm not going to do this for everyone. X cubed looks like this. It comes in here and kind of does a graph like that. Y equals x cubed looks like this. You could also put points in to figure out what this guy looks like, but he looks like this. Okay, I could do a better job here. More like this, okay. 1 over x. This is a rational function. It's undefined at x is 0. So this right here is a vertical asymptote. X equals to 0 is a vertical asymptote. And you could plug in some points to see what this guy looks like, but he looks like this on this side and this on this side. It's two parts to this. The absolute value of x is actually a piecewise function, which we'll be talking about, and you should have heard of that in college algebra as well. So it's defined like this. It's a V-shaped graph, but it's composed of two lines. One is y equals to x, which we know that looks like this, but this is only good for values of x that are to the right or equal to 0. And y equals to negative x, which is another line with a negative slope, for values of x to the left of 0. So if you were to plot this line, y equals to x, you would get this line right here. And if you were to plot y equals negative x, but you only kept it for values to the left of 0, you would get this. right here. So this is what the absolute value graph looks like. Those are our basic graphs. Now, what I'd like us to do is to go through each of these and say what is their domain and range. So the domain are the x values, and these have arrows, which mean they go on forever. So the domain for y equals to x, known as the identity function, is as far to the left as we want to go, negative infinity, and as far to the right as we want to go, positive infinity. The range is the y values that this graph will take on. So it's as low as it will go and as high as it will go. It will go as low as it wants to go. The range will go from negative infinity to positive infinity. What I'm using here is called interval notation. You don't ever put a bracket on an infinity symbol. That's why I have parentheses there. For this second graph, the domain is as wide as it wants to go from negative infinity to positive infinity. Now the range is the y values. I see no part of the graph below the x-axis. Nothing, nothing, nothing. It starts right there at 0, and then it goes on forever. So the range is from 0. So this bracket means it includes the value y equals to 0 and goes as high as it wants to go. Okay? The domain for x cubed. This is not a vertical line. It is going out a little bit, and it's going at a slight angle a little bit. So it's going to go eventually over enough time and space from negative infinity to positive infinity. And the range is as low and as high as it wants to go. So that is all reals, negative infinity to positive infinity. Over here, this is slightly at an angle, and this is slightly at an angle. These are not horizontal lines. So the domain is as far left and right as it wants to go, and the range is similar, as low and as high as it wants to go, given enough space and time. This one's interesting. It has an obvious break in it. So let's look at what we would do with this one. With this one, we can see it's got an arrow, so it's going to go as far to the left as it wants to go. So our domain starts at negative infinity, and then it goes as far to the right as it can get until x is 0. So we get as close to 0 as we can possibly get without crossing the 0 point, and we indicate that with the parentheses. This says as close to 0 as I can get. So if I could put a number here, which I cannot, but if it was possible to put a value in there, it would be negative 0.00000001. And then as soon as I pass the 0 boundary, I'm up here. I'm as close to 0 as possible. So the domain picks up just to the right of 0. So notice there's no brackets on 0, meaning it's not okay at 0, but just as soon as we get past it, it's okay. So from 0.000001, as close as we can get to 1, to infinity. The range, as low as we want to go, so that's from negative infinity all the way up to this point. This is actually a horizontal asymptote in this, and this is y equals to 0 is this horizontal asymptote. So the range is going to be as low as we want to go to this point, which is y equals to 0. So the range is from negative infinity to 0, and then as soon as we pass y equals to 0, it picks up right there, as close as we can get to 0 to infinity. So it turns out the domain and range are the same for this graph 1 over x. All right, absolute value of x. What is the domain? As far to the left will we go? From negative infinity to positive infinity. All right. How low will it go? The lowest place that we see is 0. So this is the domain, and the range, the lowest place we see here is 0. And the highest place we go is positive infinity. So this is the domain and range and how you sketch the basic graphs. Now, let's talk about something called even, whether a function is even or odd. If I look at these are all functions, meaning they've passed the vertical line test. Let's just do that real quickly. If I apply the vertical line test, can I pass a vertical line through this and have it touch more than once? If I can, it is not a function. If I can't, it is a function. So passes the vertical line test. All of these are going to pass the vertical line test. They are all functions. Now, if something's a function, we can give it another name called an even function sometimes, or an odd function sometimes. And this is not a special name, but usually they'll say neither. That's nothing special. It just means it's not even and it's not odd. If a function is even, then it will not be odd. Or if a function is odd, then it will not be even. So if we can give it an even or odd name, then that's its name. All right. So what does it mean to be even? An even function has a special kind of symmetry. Even functions, oh, okay, come on, functions have y-axis symmetry. Okay, so that means that they look the same on both sides of the y-axis. They reflect. So to determine if a function is even, you just look at it and you say, does it look the same on both sides of the y-axis? So right here, does this look the same on, this is the y-axis, right? So that's the y-axis. Does it look the same on both sides? No, I see part of the graph here and not here. So this is not even. It doesn't make it automatically odd. It just means not even. That's all we can tell. Does this look the same on both sides of the y-axis? Yes, this is an even function. Okay. Does this look the same on both sides of the y-axis? No, I see a part going up here. I see nothing over here. That's not even. Does this look the same? No. Does this look the same on both sides of the y-axis? No, I don't see anything. See, if it did, I'd see another part right there, but I don't. Does this look the same on both sides of the y-axis? Yes, this is even. All right, so these have been given the name even, so that's all they get. That's the end of them. Did I miss a graph? Oh, I sure did. I was supposed to do, let me catch up here. Here's the other one. Y equals square root of x. I thought I was missing one. All right, so y equals the square root of x. It looks like this. Again, you could point plot. The domain is 0 to infinity, and the range is going to be the same, from 0 to infinity. All right, so let's see. Is this guy even? Look on the other side. No, I don't see anything. This is not even, so he cannot get the label even. So an even function just simply means it's symmetric about the y-axis. Now, there's something called an odd function. So I'm running out of room here, so I'm going to erase this definition of what the absolute value is and write an odd function. So what is an odd function? Okay, odd functions are symmetric about the origin. Okay. How do you tell if something is symmetric about the origin? Well, this is what you do. You reflect it across the x, and then you reflect it across the y, and if it lands in the exact same place as the original function does, then it has y-axis, and then it has origin symmetry. So you don't have to do x and then y. You can do reverse order, y and then x. But if they both have that reflection, then those are symmetric about the origin. So let's have a look at this right here. Let's try this. First, let's go across the y and then x. So if I reflect this about the y, what's going to happen is this piece is going to come over here. So this is the intermediate phase. I'm going to kind of sketch this. About the y, this piece would come over here. And this piece down here would reflect over here. Okay. And then we need to reflect it about the x. So what would happen is this piece, this green piece would reflect up, and it would match right there. And this piece up here would reflect down, and it would match right there. And it did land in the same place after a reflection across the x and the y. So this one is an odd function. It met both reflection. This has already been called an even. There's nothing more to check. He's an even function. He can't be odd. How about this guy? All right, let's reflect it about the y. Okay, if I reflect it about the y, then this piece over here is going to come over here. Going to look like that. And this piece right here is going to come over here. It's going to look like this. Okay. And then if we reflect it about the x, this piece down here is going to flip up and it's going to match that black piece. And this piece right here is going to flip down and it's going to match that black piece. So this match, this is going to be an odd function. All right. How about this guy? Let's do it about the x first and then the y. Okay. If I flip this about the x, reflect it, this part's going to come down here, and it's going to look like this. Right. And and at the same time, this part will go across the X. It's going to come up here like this. All right. And then if we reflected about the Y, this piece is going to fling across the Y, and it's going to match this black piece right there. This piece is going to fling across the Y, and it's going to match this black piece, and it's going to hit right there. So this one has origin symmetry, so we can name him odd. How about this guy? All right, let's flip him about the X. If I flip him about the X, then this is going to flip up here. It will look like this. This is going to flip down here, and it will look like that. And then if I rotated about the Y or reflected across the Y, this green piece is going to flip over here, and it's going to match this black piece. At the same time, this green piece is going to flip over there, and it's going to match that black piece. So we can say that this function, 1 over x, is also an odd function. This one is even. We don't need to test him. Now, let's check this one that I forgot about. This y is square root of x. It's not even. We know that. Let's test it for odd. So let's reflect it about the x and then the y. So about the x means it would come down here. Then let's reflect it about the y. It means it would flip over here. It would end up being here after 2 rotations. Did this function land in its original spot? No, it didn't. It started in quadrant 1. It landed in quadrant 4. It is not. It did not land in the same place. So this is neither even nor odd. So this is neither one. That's all that means. Not even, not odd. Okay. One last thing for the end of this video is just take note of the odd functions. The odd functions, quadrant 1 and quadrant 3 is what it's appearing in. Quadrant 1 and quadrant 3. Quadrant 1 and quadrant 3. Quadrant 1 and quadrant 3. They are in opposite quadrants. It doesn't always have to be 1 and 3. It could be 2 and 4. For instance, let me just make up a function. First, let's say, what if I had this function right here? Okay, is this a function? Yes, it passes the vertical line test. Let's test it for origin symmetry. So if I flip it about the y, I'd have this piece and I'd have this piece. And then about the x, this would come up here, this would come down here. So this is also an odd function. So it doesn't just have to be 1 and 3, it could also be 2 and 4, but every odd function will be sort of centered at the origin and appear in opposite quadrants. So that's just something to tuck away. Okay, that's the end of this video.